Alright, one. It's June 5th. Back at it again. Alright, so earlier we did one, but I forgot to turn off my auriculares, so the audio is just terrible. Because the auriculares don't have really good sound quality in the recording. Actually, it has very poor sound quality in the recording. Much worse than the ones it's actually in the laptop. So I'm back at the laptop now, so it should be better. Alright, so the challenge today is an easy one, so it's good, so we can roll another question. What's this? Intersection of two linked lists. Given the heads of two singular linked lists, A and B, return the node at which the two intersect. If the two do not intersect, return null. It's a good question, very realistic. I think somebody might encounter a problem like this in their work. So we return C1, right? The test case is generated such that there are no cycles anywhere in the linked list. Must retain the original structure. Custom judge. What's that? The inputs to the judge are given as follows. Your program is not given these. Intersect val, the value is list B, skip A. Create a linked list structure based on these inputs and pass the two heads. If you correct, return it. Just do it, right? Basically, just do it. And this one should return. Well, what do we return? We'll return the list node. Okay, return the node. I see what it means. Okay, there are two ways to do this. I think, at least the easier way, or the really stupid way, is just go through both linked lists, and then we put the address. All right. I think, how do we get the address? Actually, I'm not quite sure. And they're not unique. Okay, they're not unique. We can put the. I'm not sure if we can put the list node directly in, because it won't know how to hash. So we can get the address. Okay, we can get the address. Well, in this case, we probably don't even need to get the address. No, we do need to get the address. So we get the address of all the list nodes, put them in a set. So we go through the first one and go through the second one, and we check. Once the address is the same, then we got it. Okay, so that's one way. In fact, let's code it that way. Okay, but it seems to me there gotta be another way to handle this. Not sure. There any like challenges at the end? Could you restore that runs in time and use O1 memory? Yeah, that's the challenge, because if you use ON memory, it's quite trivial. So what do we do? Well, in this kind of a situation, like right now, I don't have the O1 memory solution in mind. So what I'm going to do is just to try the OM or OM plus N. We're going to try that one first. Okay, we try that one first, get this one passed, and then we try to think about the other one. So there's one thing is important in my solution right now is I don't know how to get the address. It's like I forgot. Get address of object. I do not know. Oh, I asked this question in the past. So let's see. Okay. Address ID. Use ID identity. Oh, really? They only applies to CPAC. I did not know that. Interesting. ID. Okay, so here's what we're gonna do. We are going to iterate through the first one. So we can say addrs, addresses, it's gonna be a set, right? And then we just say node equals head A, while node, right? addr.add id node, okay? And then node equals node.next. Blah 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 blah. Once we're done, then we say node equals head B, and while node, if id node is in addr, return node. Right. Otherwise, say node equals head node equals node.next. Keep going. If not return, we return a what? A none? Is that what we return? No, so return none. Okay. We don't do test cases. Usually for me, almost always don't use test cases for linked list. It's difficult to write, and usually linked list is not that difficult. You should be able to write it by yourself, the correct solution. Okay, I think this one is right, and let's test both. And if they're both good, we're gonna submit it, and then try to think about what shall the actual solution be without going for the OMN, right? So we got this one, 160. Okay, that's 160. Okay, so we say this is LeetCode 160. OM plus N on time and space. Okay, so now let's think about it. How do we do O1 in space? Well, we can start, let's say we start both at the same time, okay? And move forward, and at a certain point, the short one, let me see. Gotta be a smart way to solve this. Let's see, if I have, say, 2, okay? So we start the same, move here, right? Second, and the third step. So first step, second step, third step, this one comes here, but we don't care because we don't know. And then fourth step, and then fifth step, and then boom, right? And that's it. So this one, we try to go the next, we do go next, and then sixth step, boom, one is done, right? So based on this, if we go ahead, right, and then we hit the end, we know one is how many times shorter than the other one, right? This means we can let the other one go, let's say one ahead, and then let both go at the same time. And if they are the same thing, then that's when we return. Okay, that is the solution. That is the O1 solution. So basically, we try to count, like how many, what the hell are you doing, man? We try to count how many nodes one is further than the other one. So we're gonna have NA and B, okay? Head A, head B. Okay, so while NA and MB. NA equals wait, hold on. So the short one will end first. The longer one didn't end. And then we're gonna start again. So when they Okay, so NA equals NA dot next, and B equals NB dot next. Okay, so they're gonna jump out, right? When they jump out, we're gonna say long or short, N long and N short. We say if NA, if not NB. Okay, if not NA, so NA goes out. Let's say NB doesn't go out. All right, then NA is, so we say N short, N long equals NA. What are you doing, man? If not NA, I shall restart. Okay, if not NA, which means NA is out. No. I'd say if NA, so NA is still in there. Now we need to create a new one. We can say N long, right, equals head A, and while NA equals NA dot next, NL equals NL dot next. Okay, so that's that. And then when it's done, NL will go to the first one that, yeah, they will be level, right? And then N short is equal to NB, and on head B. Okay, so that's one situation. I would say Aleph and B. Okay, Aleph and B. Then we say N long is going to be head B, while NB equals NB dot next, and L equals NL dot next, and then we say N short equals head A. Okay, else N long N short equals head A, head B. Actually, that situation can be handled here, right? We basically just say, I don't know, let's go back here. We say if NA is NB, return NA. So that handles the situation if they are the same length, which means we can go to 43, go down like this. Does not, don't need this one anymore. Okay, so basically this, I got NL and NS on the same level. All right, then what do? Then we just say while NL and NS, if NL is NS, return NL, right? And then we say NL equals NL dot next, NS equals NS dot next, blah blah blah. Otherwise, return none. Okay, let's try this one. So this was a little bit more convoluted, but I think the logic should still be sound. Yeah, let's try this. I didn't test any. Oopsie doozy. We have an issue. Wait, what is this thing? 0, I don't know. It's NL referenced before. Intersect val. There's no intersection. Oh. Oh yeah, this is not considered. Hold on. So while NA and B, they blah, 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 go to the end, and then if NA so not NA and not NB, right? Oh, it means we still need that situation. Okay, so we still need else NL NS equals NA and B, right? We still need that situation. I thought I can handle it here, but actually we cannot, which is fine. All right, let's test this one. Yep. Ooh, this is interesting. Wait, what? Hold on. What went wrong? So, N A and B, and then to the end. If this no, this no. So, oh shoot, my bad. Shall be assigned to the head. Yeah, there we go. So this is actually we need to copy and paste this thing. Yeah, apparently we don't need this. Alright, this is solution 2. So this is so long. This is O1 extra space. Right, the ideal is to run both linked lists to the end. If one of them, right, exits first, we keep running the other one, so that if we're running the other one, we reset, right? We reset now we create a new head for the other one and keep running until the other linked list exhausts. By doing this, we are able to locate the node. Well, how should we say this? We're able to make sure the two linked lists start at the same position, right? At the same position. Then once the two, then we traverse them again, and once the two linked lists have the same node, that is the one to return. Yeah, so this is OM plus N time and O1 space. Oopsie doozy. Trying to copy and paste this thing. So it's about the same performance as the last time we do it. We actually check. All right, that was 2021, a year ago, more than a year ago, March 2021. Man, time surely flies. Oh my God, look at this one. What the hell? Oh, it's exactly the same thing as mine, but holy guacamole. I see the point. Oh man, hold on. Oh yeah, okay. I know exactly what this one is doing. So we're getting close, okay? We're getting close, but not close enough. It's actually this. NA and B equals head A and head B. And then we're going to traverse and say while NA or NB, right? So as long as one of them is good, we keep going. We say NA equals NA.next if NA, right? Else head A. So we wrap around here, right? And then NB the same thing. Next if NB else head B. So we wrap around, and actually we should check if NA is NB, then we return return NA. Otherwise, keep going, and then we return none. Okay, so let's see if this one works. Actually, let me do this one first. This is my new understanding, which I think shall work. Yep, I think it works, but we can do even better. While NA is not NB, yeah. Ooh, that was so good. Wow, NA is not NB. Then we do this, and then we just return NA. So there are only two situations when NA can be NB. The first situation is NA is NB, right? The first situation that come out is both pointing to the same. And the second situation, both become none. And if both become none, that means we traverse through both and then we never find an intersection. Oh my, this is so good. This is so good. Let me write some stuff. So this is the same idea as solution 2, but Gordy. Is that how you spell Gordy? Gordy, this one is good. Two tricks, right? Two tricks are here. First, we use NA equals NA.next if NA else head A to perform the wrap around. Second, we use while NA is not NB. Actually, I think we should kind of put this one up, right? Yeah, I do think we should put this one up. So it's gonna be this, and then and this. Okay, and come back here and do this. Okay, so we use this to to make sure the only condition where the loop exits is when either NA and NB point to the same node or they are both none. Brilliant. That's really brilliant. And I'm pretty sure this one will have the same runtime, but lordy. So is there an improvement? I think so, because I don't think last time I had this. What the hell? I just kept talking and talking, and it was wrong. Is this a new test case that... Hold on, what the hell? It's the same. Okay, slightly different, but very, very interesting. 46 test cases. $39 test cases. Wait, hold on, what? That's 46. This is 39. It's the same, right? Let's copy and paste this thing and see if it times out. You gotta be kidding me. No, this is actually good. I think they are doing... I think they're doing something here. It's fine. It's fine. It's absolutely fine. Wait, why this one is not working? Wait. Interesting. Interesting. What is the difference between the two? Well, A is not B. If A is none, that is the only difference. You gotta be kidding me. What is the difference? Are you saying NA equals head A if NA is none, else NA dot next? NB equals head B if NB is none, else NB dot next. Are you telling me this one passes? No, this one does not pass either. Oh! Man, I see what happens there. You need to switch. Wait, hold on. So we start and then one of them get to the end and we jump back. So the whole purpose is if one of them go to the end, we'll keep running the other one and then we start from this again and then we know where this is and then we need to swap. Oh, that's head B, that's head A. I don't know why this one passes. Oh my god. Important. Don't forget to swap. Within the loop. It makes sense, right? It makes sense if you think about it. If we say we want to completely follow solution 2, when one of them go to the end, right, and the other one still have something left, the purpose is to find out the equal starting point, where that is on the longer linked list. So we need to put the first one, when it hits the end, to the beginning of the second one, and then we keep running. I don't know why I just didn't get that one right. It's quite embarrassing, to be honest, but now we know. My lord. My lord, I was going through too fast. See, this is a good problem. I think I had exactly the same issue here. Did we get something similar? I don't remember. Oh, look at this. Nice. This one used to have a solution. Now the solution is locked. Ah, the benefit of doing this already. Yeah. That's a good problem. That's a very good problem. All right, so okay, I put that behind us. Put that behind us. Let's see, we got 30 minutes. 30 minutes for one problem. Gordy, that's not fast. All right, k divisible elements subarrays. Given an integer array nums and two integers k and p, return the number of distinct subarray. Okay, subarray is contiguous, which have at most k elements divisible by p. So we have k and p, right? We want to know the number of distinct subarrays which have at most k elements. At most. So it can be smaller or equal to k, divisible by p. Two arrays are distinct if they are of different lengths or there is at least one index where this nums 1i is not equal to nums 2i. This two arrays are said to be distinct if they're the same length, then they exist at least one index I. Subarray defined as a non-empty contiguous sequence, right? So subarray. I mean, think about it, you're getting it from the same one. And can we have? No, we cannot have like 2 and 2, right? They only have 1. Yeah, so we want the subarray to be distinct. So we put them out and we say if they're the same length, then at least there are 1 index and they're not the same. Okay, that's fine. That's something we can do. Length is 200. Okay? Length is 200. So there are a lot of solutions out there. So 0, 3, 4 are divisible by 2. 11 distinct subarray which have at most k equals 2 elements divisible. So we want to include 2. At most 2. So it could be 1, could be 2. So 1 is just 2, 2, 2. Ooh. That's only 1. Right? And then, oh, we can get higher. 2, 3, 2, 3, 3, 2, 3, 3, 2. And 3. 0. 0 can be at most k. So it could be 0, 1, or 2. Oh my god. 3, 3, 3, 3, 3, 2, 3, 3, 2, 2. And then 3, 2, 3, 2, 2, and 2, 2. Because it has 3 values. Okay. Oh, that's everyone. Every subarray. All right. Now, here's the thing. Because it's at most k, 0 is included. So, no matter what, single length will always be good, right? Except when k equals 0, right? When k equals 0. If k equals 1, which is a single one, it's always good. What you saying? We can do. We need to find the ones that's divisible by p. Okay. So edge cases. K equals 0. We don't need k equals 0. We can do k is 0, k is 1, k is 2, like that, right? We just go k is 0 because we have to calculate k is 0 no matter what. So we get the indices where the one's divisible, okay? So a bunch of signposts in this array. Like we have a bunch of signposts that are divisible by p. And then everything in between, okay? Everything in between are not divisible. So they have 0. So all of them, all the combinations of them, which is just the length k, which is k plus k minus 1 plus k minus 2 all the way to, I shouldn't say k, m plus m minus 1 plus all the way to 1, right? So it's 1 plus m times m divided by 2. So that is the total number, right, within that, okay? So these are like islands, okay? Now we say we want to include, so we start from these islands, right? But we have islands of non-divisible, so basically we have islands of non-divisible, contiguously non-divisible, and they're separated by the values that are divisible, right? Now we want to include 1, so basically just everything in this, okay, we say we include 1, and when you include 1, I can include counting left, or I can include counting right, and that just 1, 2, 3, all the way to m. We have m of them, right? We have m of them. Hold your horses. Hold your horses. How do you handle duplicates? Damn. Good question. How do you handle duplicates? Oh man. Oh man. Duplicates. Tuples. Tuples. I don't care. Do not care. Tuples. Because we only have 200, right? So I'm just going to tuple all the way. Tuple all the way. Yep, we're going to tuple all the way. So basically what we're saying is for each island, right? For each island, we have starting, and then starting 2, starting 3, starting 4, whatever. So we put this in it. And then we know, starting from this, how many uniques, right? How many uniques. And from the second spot, same thing. How many uniques? We always count into the right. How many uniques? How many uniques? How many uniques? So we get the number of uniques starting from this position. Question. So we can count both ways. Lordy. You kidding me? Are you kidding me? Oh no, I'm not kidding you. I see it. I see it. I think I see how this one going, but it's just a little bit complicated. A little bit complicated. All right. Calm down. Calm down. So, what do we need? We need to know, starting from a position, right? Starting from a position, going right or going left, right? Because the boundaries, those are the important ones. So we find out. We find out the signposts. Okay, I'm just trying to see step by step how can we do this. We find out the signposts, okay? And then after signposts, we will get the islands. So we get one island out. Then we're going to count how many uniques there are. But we also want to know how many uniques there are starting from the left edge and starting from the right edge. So it's from the left edge going right and the right edge going left. So we're going to have something called left edge, which is going to be a dictionary. We have the index and the count. Okay, so all the left edges will be here. And we're going to have another one called right edge, right? On the right edge is all the right edge index, we're counting left. So we have all this data structure of the left edge and right edge. And we're going to count all these, which is totally fine because that's just a zero. I have a zero number divisible by the p, which is perfectly fine. And now we're going to start to say while k is larger than 0. No, while k is larger equal to 0, right? And then we are going to say, no, we'll just while k larger than 0. And then we start dropping down. 1, right? So we want to find 1. If we want to find 1, we just go through every single one, right? Every signpost. We have the first signpost, and then signposts are just an array of indices. So we find the first signpost, we go left and go right. Right? That's it. Yeah, that's actually basically it. We go left and go right, and we look into the left edge, look into the right edge. Boom, done. K equals 2. So we need 2. So consecutives, pairs, right? We have pairs. Or we have pairs, we go left and go right, go left and go right. And 3, we can have to include 3. Go left and go right, go left and go right. Question. We still run the risk of uniqueness. Corey, you're killing me. You're killing me here. Like seriously, you're killing me here. Set. All right, we're not going to do count. We're going to actually put all the set out. My, oh my. Ooh. Hold on. I'm going to stand up and walk around. I'll come back soon. I think set is the only way to go. Because otherwise I cannot analyze my way out of this uniqueness. We're going to do sets. Decided. Set is the way to go. Now again, this one is, I don't think it's tough. It's just, there's going to be a lot of edge cases. I don't want to turn this one into one of those problems where I just debug, trial and error to get to the correct answer. But no, I don't want that way, right? I don't want that. I don't need that on my conscience. So what we're gonna say is posts, signposts, SP. I don't think I even know what SP stands for. Let's go signposts. Okay, signpost gonna be I for I n in nums. If n mod p is equal to 0. So these are my signposts, right? So we're gonna go between every signpost and then produce a left and a right. Actually, we're gonna have an overall, because we're set, which is fine. I'm gonna say rest set. Okay, that's gonna be a set. So what do we do? Signposts for each pair of signposts, right? What do we do? What do we do? We do left and right, and then we do in between. I don't like that. I do not like that. I don't think that's the right way. So what I'm going to do is I'm going to put -1, okay? I'm going to make it such that I'm going to do this one. Signpost equals -1, okay? And then for I n in nums, if not I n mod p signpost dot append I, right? That's when we're done. We say signpost dot append len nums. So we put another signpost around them, right? Then we can always say, right? We can always say, so we're gonna produce all these things. But hold on. Oh man. Let me think again. So what we're saying is starting at this position, right? We have that, and we have that, and we have that, and from and we you want to be stupid? I don't know. I don't know. What do we do? What do we do? Like seriously. I'm not gonna hold on. No. Mm. I'm gonna do the most stupid thing. Okay? The most stupid thing. We're just gonna go find the first one and just go through everything. Alright? Find find the second one, go through everything. Find the third one, go through everything. And then go through all of them without the signposts. Which window? You're welcome. All I see is lots of repeated things. But I don't know. I don't want to analyze. That's the thing. I think to analyze is not gonna work very well. So for each one we go left and we go right. For each one we go left and we go right. This one will go left and right. This one will go left and right. Yeah, that's fine. Okay, let's just say for I in range, let's call it j. I like to get j in range 1 to len signposts -1 because we have padded them on both sides. So what do? What we do is for each one coming out, right? For j coming out, we're gonna go left and go right. So we're gonna say for k, we'll have a k. For a, right? We're gonna say for a in range j -1, okay? J -1 to 0, okay? And wait, hold on. It depends on how many. That's just 1. I'm gonna have to go back to the 2. Man, hold on. It's like we have a range, right? We need a range. No, we still do that. We still do it, right? We still do it. We still save it. It's still useful. We're gonna do both things. Okay, we're gonna do both things. Hold on. So I have to check one more thing I forgot. Can I add tuples? I can. No. I need to get. Yeah, here's the thing. We're gonna find all the zeros. Okay, we're gonna find all the zeros. So we're gonna say for I in range to len signposts -1. Okay, and I need to have a dictionary. We call it L edge, and that should be a default dict of list. Okay, I don't care if they duplicate. That's not my concern. My concern, I could just say L and what do you mean? What do you mean by L and R? L is left edge, so yeah, so L edge, I should say L edge, right? And this is right edge. That's also a default dict list. Okay, so now we have the signposts, right? the signposts. So what we can say is L and R, right, is equal to signposts I. Signposts I, that's signpost plus 1, and a signposts I plus 1, right? Because we do pairs. I plus 1, and this thing minus 1. So that's the boundary of L and R. So what we're gonna do, right? What we're gonna do is, I don't do this. I don't do this. What I do is going from left to right. Find all that start from L, find all that ends at R. Put them in L edge and R edge. Okay? And they're all tuples. But put everything inside the rest set as well. Hold on. Is K smallest to be 0? K smallest is 1. Okay. So for J in range, okay, L to R plus 1, right? That's J can go for I, J, K, L, and then I said H in range. So J from J, so they can be the same. J to R plus 1, right? So for that, we're gonna say temp equals tuple. Tuple what? Nums what? J to H plus 1. Right? From J to H, J to H, J to H. So tuple gonna put this in, right? We have this. And we say if J is equal to L, right? If J is equal to L, say L edge dot L edge L dot append temp. If H is equal to R, right edge R dot append temp. Yep, we'll just go through this. This will build up our library. These are our libraries, okay? Our library will have a left edge, right edge. Done, okay? Then we're done. And then we're gonna start, right? We say for Q, I don't know, just pick whatever number. For Q, I would say KK. Okay, how about that? For KK. For KK in range 1 to K. That's the number we have to add, right? That's the number of that. So from 1 to 2 to 3, whatever, okay? So now we say KK is 1, okay? If KK is 1, then we go through every single one by themselves. What if a KK is 2? What we're gonna do? So we have a base, right? We have a base. So base for, oh my gosh, how many are you going to do? Let's reuse some stuff for I, okay? That's the starting point, okay? For I in range, I don't know, from 1. Do I even need to add these endpoints? Why do we add these endpoints in the first place? Oh, I know why. Hold on. Nah. That shall be signposts. I have to go to the end. So I is here, right? Then plus 1 and I plus 1 minus 1. Does look like do this. So we start from the most left. That's the first signpost. And we want to find every pair of signposts. Yes. And then from here, K, and then right, and then for I, we're looking through the signposts. So from 1, yes, okay, all the way to what? All the way to something, right? Depending on the KK. And we're going to use, let's say we do this, and we're starting from here, and we say how many do we cover, right? So KK has to be len signposts minus KK. That's what I think, because if KK is 1, right? If KK is 1, that's actually going to be minus 1. If KK is 2, right? Because we have a dummy at the front and a dummy at the end. Right, so if KK is 2, then it can be signpost minus 1, right? Signposts minus 1, minus 3, minus 1, minus 2, minus 3, and be here. Right, that's the actual thing that we will hit. And then this we can go if KK is 2, this and this. Okay, so I think this is correct. Okay, so that's I. And we're going to build a base. Base is going to be, we can actually go tuple again. Nums I. Oh, that's not nums I. And then signposts I, right? From signposts I to signposts I plus KK. Right? If it was 2 plus 1 plus 2, so yeah, sign plus KK. Okay? So that's the base. So we have the base. Now we look left and look right. How do we look left and how do we look right? And I just realized one thing. Is this correct? Yes, this is correct. So we need to look left and look right. So we have a base, and the base, the starting point is I. Oh, actually, let's be even more explicit, right? So when you say low and high, this one, low and high. Low is I, high is I plus KK, minus 1, right? If we want to say the actual index is I plus KK minus 1. And that's actually not true because it's signposts I and signposts this thing. That, my friend, is the actual thing. I plus KK minus 1, that is the signpost. So we have the low signpost and the high signposts. And come back here, right? It's going to be low to high plus 1. Low to high plus 1. So that's the base. So now we find the base. We can go, right? We can go on the right edge and the left edge. Just within them, right? Just within them. How do we do this? So we're going to say add right edges. Okay? So that means for RE in right edge, what is that? That is low minus 1. Okay? That is low minus 1. Because low is the signposts. So signpost minus 1. Yes, so we're gonna say, what the hell happened? 26, right? For right edge. So we have one right edge, 2, 3, 4, doesn't matter, right? We don't care. So everything we're gonna say resset.add. Okay? And where is resset.add here? My bad. I forgot to add resset.add temp. Okay, so reset.add. Add what? Because it's the right edge, go to the left, and then be this plus nums. Oh, no, base. This one plus base. And then we say this actually can go to the here, right? And for left edge, in left edge, so what's this left edge? Left edge is going to be high, right? Because it's high plus 1, right? High plus 1, because high is the signposts, okay? High is the signpost, so high plus 1 is going to be the left edge. So I'm going to do that, and the rest set.add base plus this. And I just realized one thing. Oh my god, there's one more thing. There is one more, because you've got to be kidding me. There's one more. I can go like, this is a signpost, right? If I have something here, it can be something 2, 3, right? Something 2, 3. You're killing me, man. You're killing me. You're murdering me. My god. Calm down. So basically we say we get the left edge, right? So every time we get the left edge, we go right edge from 0 to 1. Okay, that will work. That will work. So we got right edge for left edge in L edge I plus 1. But there is no empty. Okay? There ain't no emptiness in this. We need empty. We need empty. Lambda, I'm going to return the list with an empty tuple. I think this should be fine, right? This should be fine. This is an empty tuple. Actually, no. Is this an empty tuple? No. Yeah, that's a tuple. So I need it to be an empty tuple. And then we can keep adding to it, which is fine. No, it's totally fine. But it has to be an empty tuple. Now, because we have empty tuple, so the first one coming out will be an empty tuple. So that's empty, and that's empty. And then we can do them adding together, right? This is add left edges. And then that's going to be right edge plus base plus left edge. So it'll be empty, empty. So we're going to do this plus, let's say 1, 2, 3, plus this. Just the base. And then the left edge will grow. We're going to just extend it to the left, and the right edge. Okay, so that's that. Okay. Is that it? And then once we're done, return the length of set. So basically this is completely not ignoring. Right? Completely ignore a analysis. There's no analysis. Completely brute force. Brute. Absolutely brute force. Alright, so here's the deal. We are going to, for sure, try our best to see if it works. Say change. Okay, so we can say find next, delete two words. Okay, fine. Then p equals delete two words. Next, delete two words. Okay. Alright, so we change this. What's this gonna be? Num kp. Okay, so nums k and p. Next, back. What's this? Count, distinct, go. Cannot unpack, non-iterable, int object. What the hell? Wait, what? I don't know. I just kept forgetting to write this. Oh, and right, 11 and 10. We're missing. Not missing. Let's see. Print res set. What do we got? We're supposed to have 11, but I got 8. Oh, I'm missing quite a few. Wait, hold on. We have 2, 3, 3. Okay. 2, we got it. 2, 3, we got it. And 3, 3, 3, 2. 3, 3, 3, 2. 3, 3, 3, 3, 3, 2. Okay. 3. 2, 3, 3, 2. We're missing 2, 2. We're missing 2, 2. Hold on, let me think again. I feel like we're very close. We're very close, but we need to get. So first of all, let's see the signposts. The signposts are right. -1, 0, 3, 4, 5. Yeah, signpost is correct. Okay, so now we're gonna do is let's print it on R. Actually, I want to do it after so we can check. So I'm going to print LR, right? And I'm going to print L edge and print R edge. Lordy. This is not right. Signposts. How is Wait, what? Signpost is this 0 minus 1 is 0, right? And then the left is minus 1 plus 1 is 0. Wait, hold on. We have the signpost is minus 1, 0, 3, 4, and 5. Okay? Now, we say we want to find the left and the right, right? So the left is going to be pointing here. The right is going to be, because we start from here, this one minus 1. So the right is there. So because of this, there ain't nothing. Right? We say, because it's empty. Right? It's empty. So we say if L is larger or equal to I, R, then we continue. Okay, so when that happens, this one doesn't do. And then one, two, and so just 0 and 3. Interesting. Very interesting. That is actually correct, right? That's actually correct. So in this case, hold on, we have 2, 3, 3, 2, 2, and then we have 2x right here. So what we have is, actually we can print it out at the end. What we have is on the left edge, right, is one, we have an empty, 3, and 3, 3. Correct. On the right edge, we have a 2, empty, a 3, and a 3, 3. That's correct. Okay? So now we need to construct. All right, construct. What are we missing? We're missing 2, 2. 2, 2 something, right? 2, 2 something. So basically, we have 1, and the problem is with 2. Okay? So, problem is 2. So kk equals 2. Let's find out. Let's find out low and high. Let's say print kk low and high. Okay? So kk is 1, low and high. kk is 1, low and high. Hold on. Oh, signposts. Now, low and high is the actual thing. So low and high is 0 and 0. 3, 3. Why not 4, 4? I'm just asking, why not 4, 4? because I can take, so signpost, this is signposts. Signpost is -1, 0, 3, 4, and 5. I can take 0, I take 3, but I didn't take 4. I think that's the reason why it is not right. Land signpost, so 1, 2, 3, 4, 5. 5 -1 is equal to 4. Right, 0, 1, 2, 3. So you're telling me I should have -1 here. I should not -1. Let's put the other one. Okay. We might have something. Let's try. Alright, when they run it once, if it fails, that's it for today. We're going to try it again tomorrow. I hope it does not fail. I hope it does not fail. Come on. Come on. Alright, so we'll do this tomorrow. Expect 27. No, we're missing a lot. Alright, we'll do this tomorrow. I'll see you guys tomorrow. Adios.